Good afternoon, everybody. Welcome to TACO Tuesdays. This is the first in the commercial series of our webinars that we have planned, one a month for 2020. Very exciting. My name's Brett Zerba, and I am an applications engineer with TACO. Before we get too far into today's presentation, if you would please look on your screen and raise your hand if we just want to make sure we are being heard by people. And if I see some hands come up, I do see some hands coming up. I appreciate that. So I do believe we are broadcasting. So that's always a good thing to know. So again, welcome to TACO Tuesdays. It's a new series started in 2020. There's going to be two a month, one more focused on residential or wholesale, and one more focused on the commercial side. So the first quarter schedule is up and available at on our website, and look for the remaining schedule hopefully by the end of the month shortly. So today's webinar is going to be on expansion tanks. Rich Medairos, my co-conspire presenter here, is going to take it away very shortly. We are looking forward to today's presentation. As we go throughout, we will work some questions in, so hopefully everyone can figure out how to ask the questions. Feel free to ask them, and we'll either work them in during the presentation or towards the end. So there'll be plenty of times we feel for questions. A couple other things. Tomorrow, after the webinar, you will receive a email thanking you for attending with a link, and that link will give you access to a video or a taping of today's webinar, as well as access to a download so you can get your PDH hour credit if you would like to get a certificate for that. So please look for that for tomorrow, and if you don't get it for some reason, contact us through the TACO website, and we will make sure you get that. Also, on the TACO website, there is a kind of a page pertaining to TACO Tuesday, and that will also have, you can see the videos there as well. So there will be access to the video on the website as well. Just a friendly little statement here. TACO, it is TACO. It's not taco. Some of you may think that the word is taco, but up here in the Northeast in Cranston, Rhode Island, we like to say tacos are for eating and TACO is for heating. So I'm going to turn it over to my friend Rich, and that's the end of my verbiage here. You will hear me towards the end or when there's questions. Other than that, Rich, take it away.
Thanks, Brett. Good morning, everyone. Actually, good afternoon, everyone. I'm broadcasting from the East Coast. So some of you that are listening in on the western part of the country, or perhaps in other parts of the world, have a different time. Just a quick check, just to make sure that you can hear the audio and you can see my screen. Just want to confirm that before we get started here. I'm going to assume, Brett, that you can hear me okay.
Rich, I can hear you fine, and I can see your screen.
Great. If you could stay on for just a moment and make sure that when I at least go through change my first slide, that it's broadcasting properly. So again, welcome everyone. Today's topic for the webinar is expansion tanks. And before I get started, one of the reasons that we like to do this webinar is because expansion tank information and knowledge is one of our most popular presentations. We have probably more people asking questions about expansion tanks than any other individual product or application. So let's get right into it. In terms of our presentation today, we're going to talk about the types of expansion tanks, and then we're going to talk about expansion tank sizing, and then we're going to deal with questions. Now, it seems like we only have a couple of topics, but when we get into it, we'd like to try to dig into these topics in a lot of details so that you can gain some information. So let's get right into it. What about the types of expansion tanks? Don't worry so much about the narrative here. I will be showing you photographs in a minute, but I just want to list them out before I show you the photographs. So types of expansion tanks, the first type is called a plain steel tank, and I will again have some photographs to share with you. The second type is a bladder style tank, and bladder style tanks come in two categories. One is called a full acceptance tank, and the second category is a partial acceptance tank. And I'll get into those definitions in a little bit more detail. And then the last type of expansion tank are diaphragm style tanks. And diaphragm style tanks only come as partial acceptance tanks. Okay, great. So those are the different categories and types of expansion tanks. So let's take a look at some photographs to see what they look like. So the very first one is called a steel expansion tank, otherwise known as a plain steel tank or PSS. And these tanks are, as the name implies, they're just a steel container. I will mention that all of TACO's expansion tanks are ASME certified, and this plain steel tank is also ASME certified. And if you'll notice, the plain steel tank only has 4 connections. At the bottom, it has the connections to the piping system, and on the left side, it has connections for sight glass. So a plain steel tank, as the name implies, does not have a bladder inside. And so one of the limiting factors of an expansion tank is you cannot pre-charge. You can't put any air into the tank. There's no Schrader valve. There's no place to pre-charge the tank because there's no bladder to separate the air from the water. Okay. The second style, probably the most popular style, is called a bladder style tank, and it's called a full acceptance. And in the world of TACO, that's our CA models. Now, if you'll notice, I have 2 photographs. The red ones in the just to the right of center here are the way the tanks look like when they're shipped from the factory. And then on the far right, you'll see a photograph of a cutaway of a steel bladder style full acceptance tank. And the black material that you can see hanging down from the top is the bladder. You can sort of think of the bladder as a balloon. And then the space between the outside of the bladder and the steel container is where the compressed air goes. And so the air and water are separated by the bladder. And the other thing, which you should be able to decipher from this photograph, is that the bladder is a full acceptance. And by definition, that means that the bladder can expand to the full volume of the steel container. So for example, let's assume for a moment that this steel container is 100 gallons, and the bladder itself could be filled with water, and that bladder could expand to the full volume of the steel container, or I could put 100 gallons of water inside the rubber bladder.
Hey, Rich.
Yes.
Before you get too far, here's pretty much a question that we need to cover. Can you give a brief definition of what an expansion tank actually is, maybe system-wise, or what's it for?
Sure. So an expansion tank allows the fluid inside a hydronic system to have a place to go when the fluid expands as a function of temperature change. So typically when we fill a system, it might be in the range of around 50 degrees Fahrenheit. And then if it's a hot water heating system, the fluid, in this case, water or water glycol, would expand as the temperature increases. And if we didn't have a place for that water to expand to, it would break the components inside the system. So the expansion tank allows the fluid to expand and have a place to go. It also controls the pressure in the system, and that's a critical part of a hydronic system operation. It controls the minimum and the maximum pressure, which we'll get into some detail. So Brett, does that answer the question? Okay, I'm going to assume it does, and I'm going to continue along here.
Sorry, Rich. Thank you. That does. And just to confirm, the water goes inside and the air is on the outside of the bladder.
Correct. So the water enters the expansion tank, and this specific one on the inside of the bladder or the balloon that holds the water, and then between the balloon and the outside of the balloon and the inside of the metal container is where the air goes. Great question.
Thank you.
Okay, so the next category is called a partial acceptance. And again, you can see the red photograph of the partial acceptance tank. And then you can see the cutaway. The bladder is much smaller in this tank. Now, a partial acceptance tank means that the bladder does not expand to the full physical volume of the sealed container. Again, using our example of 100 gallons, the steel container may have a volume of 100 gallons, but the bladder perhaps only expands to some percentage of that. And we'll get into the details, but let's assume for this part of the discussion that the bladder has 50% of the steel container. So if the steel container holds 100 gallons, we can safely put in, if the bladder had 50%, about 50 gallons. So typically in a partial acceptance tank, the bladder can only expand to some percentage of the full steel container. And in our series, those are the CBX. Okay, the next category is called a diaphragm style tank. And again, if you look at the photograph on the right, one of the things you may or may not realize is that the water in this case enters the tank at the bottom, and the air enters the tank at the top. And so when the water enters the tank and it expands, it pushes the diaphragm upward. The diaphragm is connected to the inside of the steel tank along its circumference. The main difference between this style and the previous styles is that the diaphragm cannot be replaced. If it should fail for any reason, then the tank has to be disposed of. It cannot be repaired. The diaphragm cannot be replaced. Let me just go back and highlight the first two. In the full acceptance CA bladder, that bladder can be replaced, and also in the CBX, the bladder can be replaced. But in the diaphragm style tank, the bladder cannot be replaced. So hopefully, if anybody has any questions, they can forward them to Brett, but I'm going to move on to the next part of the discussion. And that has to do with expansion tank sizing. So when you size an expansion tank, you need a minimum of 5 pieces of information.
Hey, Rich, before you go too much farther, I've got a message that the sound has gone out. I can hear you fine. Can some folks wave their hand again if they're still hearing me? Okay, I see people waving. So, or send me a note or something. Okay, all right, never mind. Yep, we're all set. Thanks.
Okay.
Back to you, Rich.
So in expansion tank sizing, we need to collect 5 pieces of information. We need the minimum or fill pressure. We need to know the maximum pressure. Again, these are the water side pressures in the expansion tank, and you'll see how they relate to the air side in a moment. We also need to know the minimum temperature, sometimes referred to as the fill temperature, We need to know the maximum temperature. We also need to know the system volume in gallons. Now, there's a couple of other pieces of information which we should know, and when we get into the actual application and selection of an expansion tank, you should also know the piping system material, whether it's steel or copper. And you should also know whether or not the fluid is 100% water or if it's a water glycol solution, for example. Okay, so let's get right into an example here. Given a 75-foot tall office building in this example, let's find the expansion tank size. And I've got a little diagram here that indicates what an office building diagrammatically would look like. In this case, it's got 5 floors. The floor-to-floor height is 15 feet. 5 times 15 is 75 feet. The other thing I want to point out is for this first example, the mechanical room is on the first floor or the lowest part of the building. Now, since the building is 75 feet tall, we can figure out what the pressure would be inside the piping system if the piping system had a total vertical height of 75 feet. So let's look at the mechanical room on the first floor. It's a very simple diagram. It indicates that we have some piece of equipment. On the right-hand side of the picture here, you can see IHL, which stands for imposed heating load. Could be anything from a fan coil to an air handling unit, any kind of mechanical piece of equipment. And that piece of equipment has a certain pressure rating. If we move from right to left, we can see a safety relief valve. A little bit farther to the left, we can see a pressure gauge on the discharge side of the pump. We can see a pressure gauge on the suction side of the pump. We can see, as we move again to the left, the fill valve, pressure regulating valve, and then also the expansion tank. So the first piece of information that we want to figure out is what is the minimum pressure at the expansion tank. So that's the first piece of information that we're going to try to hunt down, is the minimum pressure. Well, it turns out that the height of the building converted into pounds per square inch gauge is simply, in our case, a building that is 75 feet tall, and we divide by the conversion factor of 2.31 feet per pound per square inch gauge equals 32.5 pounds per square inch gauge. So I'm going to go back to my diagram for a moment because I want to point out back to my building diagram. Again, the building is 75 feet tall. The assumption is the piping goes from the lowest level to the highest level. Now, I understand that piping is probably not going to sit on the physical floor of the building, but we're sort of taking the worst case in our 75-foot tall building. So the conversion between the pressure in feet of water column and pounds per square inch is that there's 2.31 feet for every pound per square inch gauge. So let's go back to our little equation here. So we have, if we fill the piping system with water, and let's assume that we have a valve at the very, very top of the piping system inside of our building, and we can open that valve and purge the air out, and we slowly fill the system so that just a drop of water comes out of that valve at the very top, and we stop filling it. The valve is still open to the atmosphere. The pressure at the bottom of this building at 75 feet tall is going to be 32.5 pounds per square inch gauge, 32.5. The pressure at the top, in terms of gauge pressure, is 0. We haven't pressurized anything. The valve is still open. All we did was we filled the piping system. All the air came out And eventually we got one little drop of water out of our valve that was located at the top of the building. So the next question is, how much pressure do we want when we close off that valve at the top of the building? So use your imagination for a moment. We close the valve off at the top of the building and we start to pressurize the system, but what pressure do we want at the top of the building? Well, most people will say that they want somewhere between 5 to 10 pounds of pressure at the top of the highest point of the building. In this case, we're talking specifically the highest point of the piping system. So most people will pick 5 to 10 pounds. Well, why do you want somewhere between 5 to 10 pounds? Well, for two major reasons. The first one is that you want to have enough pressure at the top of the building to purge the air out of the system through air vents. If you didn't have any pressure at the top of the building, if you had an air vent, the air would have no way of escaping because there's not enough pressure to push the air out. And the second reason is that we do want to have some pressure at the top of the building to ensure that if we have any equipment at the top of the building, for example, a pump, especially in hot water systems, so that we don't run into the issue of having cavitation as a function of net positive suction head. NPSH, or net positive suction head, is really set aside for another discussion in the future. But the important thing is that we do want to have pressure at the top of the building. And since most people would like somewhere between 5 to 10 pounds, for this example, I want the math to come out simple. I chose 7.5 pounds at the top. If I have 7.5 pounds at the top of the building, top of the piping system, I add that 7.5 to the 32.5 because of the height of the building, and that means that my minimum pressure at the bottom of the building is 40 pounds per square inch gauge. Now, this is a very important concept. So let me repeat. If I have 40 pounds per square inch gauge pressure at the bottom of my piping system, then at the top of my 75-foot piping system or 75-foot building, my pressure at the top is going to be 7.5 pounds. So since that's between 5 and 10, that's more than enough pressure to purge the system of air. And in most cases, it will be enough pressure to offset any possible cavitation that could potentially happen for a pump. Okay, so now we know what the minimum pressure is in the building.
Hey, Rich, how does, I'm going to ask this question now, minimum pressure. If the expansion tank's located at the top of the building, I know it affects the numbers, but how does it affect the minimum pressure?
Well, if you move the expansion tank to the top of the building, the minimum pressure would be that 5 to 10 pounds that we said. In this specific example, if we move the expansion tank to the top of the building, it would be at 7.5 pounds per square inch gauge. So by moving the tank from the lowest part of the building to the highest part of the building, it changes the minimum pressure required at the expansion tank. But our expansion tank is located physically at the bottom of the building, so it needs to be 40 pounds per square inch gauge. Now, let's go back to our building. Just a reminder, our building is 75 feet tall. Our pressure at the top is 7.5 pounds. That 75 feet translates into 32.5 pounds plus the 7.5. So I'm going to have 40 pounds at the bottom of the building. So there I am. Now you can see the minimum fill pressure is 40 pounds per square inch gauge. It's also known as the precharge for the tank. Now, when we ship expansion tanks from the factory, we ship them at a pressure of 12 pounds per square inch gauge. So if you were connecting this expansion tank to this system, before you physically connected the expansion tank to the system, you would have to precharge the air side of the tank through the Schrader valve, which is located at, in this case, on the steel container side of the tank, to 40 pounds per square inch gauge. And the reason you need to do that is that when you connect the expansion tank to the system, if the fill pressure is set at 40 pounds and the pre-charge was still at the factory setting of 12 pounds, then what would happen is that the 40 pounds of pressure in the system would start filling up the bladder and would not allow you the full expansion that you're looking for. So pre-charge is a very important concept. You must pre-charge the expansion tank to your minimum or fill pressure before you physically connect it, and you're adding compressed air to the air side of the expansion tank. Okay, let's go on to the next point. What about the maximum pressure? Well, there are several methods that people use to determine the maximum pressure. I'm just going to show you one of those methods. So back to our little piping diagram, let's assume that the equipment that's at the lowest part of the building has a maximum design pressure of 150 pounds per square inch gauge. So I never want the system to have that much pressure at that piece of equipment. So I'm going to work backwards from that point. If you notice, I have a relief valve. I tend to set the relief valve at about 10% below the maximum. Each engineer will have a different set of criteria, but I always want to make sure that my relief valve setting is below the rating of the equipment. So I would pick roughly 10%, 150 minus 10% or minus 15 pounds would be 135 pounds. So that's what I would set for the relief valve. Safety relief valve set at 135 pounds per square inch gauge. Now, relief valves are very simple devices. They basically have a disc. That disc is held closed through a spring, so they're not all that accurate. So if you get close to the setting of the relief valve, in terms of pressure, as I approached 135 pounds in the piping system, let's say I get to 134.5, then that valve could potentially start to leak or weep, drip water out of it. So to ensure that the valve is not going to be close to its setting, the pressure rather, in the piping system is not going to be close to the setting of the relief valve, I'm going to make sure that the piping pressure is going to be a maximum of about 130 pounds or 5 pounds below the safety relief setting at the discharge of the pump. Now, generally speaking, this is not an absolute number, but it's generally speaking the maximum pressure that a pump can generate is its shutoff head. So let's assume that this pump with zero flow can generate 20 pounds differential pressure across the pump. That means to ensure that my discharge pressure never gets above 130, I want my suction pressure to be 110. Excuse me, losing my voice here. I'm just going to take a quick swallow of water. Sorry about that, folks. So the suction pressure at the pump wants to be 110 pounds. So now I'm going to work from left to right just to show you, be a bit repetitive, but to show you what we're talking about. If the pressure at the suction side of the pump is 110, if for some reason someone should shut some valves off and they isolate the air handling unit, in this case, which is 150 pounds, the pressure at the pump will develop 20, that's 130. I want the relief valve to be set roughly 5 pounds above the maximum that's in the system, and I want the relief valve to be set about 10% below the maximum pressure of the equipment. So in this case, my maximum system operating pressure before the pump is 110 pounds. Now I have two pieces of information to help me size the expansion tank. I have the minimum pressure or fill pressure, and I have the maximum pressure at the expansion tank. Okay,
hey, Rich,
let's go.
Rich,
yes.
Before you get off that one, what exactly is the location? What's your recommendation, or should the relief valve be located? Is it after the pumps as shown?
Well, again, the relief valve could potentially be located almost anywhere in the system, but in most cases, it's probably attached to either the system, the relief valve shortly after the pump, or in some cases, it might be physically connected to, for example, a boiler will have a relief valve. If there is a heat exchanger in the system, in this case, we have an air handling unit, conventional sort of heating coil. But you could have a shell and tube heat exchanger, for example, that steam is being fed to the shell side and the water side. In this case, it would be the hydronic side. There would be a relief valve on the water side to prevent the water from developing too much pressure. So it depends on, it's system dependent. In my case, I'm showing it after the pump, but in some cases, again, it might be connected to the boiler or some other piece of equipment. Okay, so now we have both the minimum or fill pressure and we have the maximum pressure. By the way, the maximum pressure, you can be very conservative. This is the maximum pressure I'd like in the system. There's nothing that says that I can't have a maximum pressure slightly lower than that. I want it to be above the minimum pressure because it will affect the size of the expansion tank. And in this case, I've estimated that the maximum pressure at my expansion tank should be 110 pounds, but I could just as easily make the maximum pressure at the expansion tank less than 110. I could make it 100 pounds if I wanted a little bit more safety factor. Okay, the next piece of information we need to gather is the minimum temperature, again, sometimes referred to as the fill temperature. Well, most buildings are connected to a municipal water supply. And even if they're connected to a well water supply, that water temperature tends to be the groundwater temperature. Well, in New England, where I'm from, the groundwater temperature is relatively constant at around 50 degrees Fahrenheit. In other parts of the country, it could be slightly less. But generally speaking, the water temperature is between 40 and 50 degrees Fahrenheit. And that becomes the temperature of the water that you're filling the system, or the minimum temperature. The maximum temperature is whatever is set by the equipment. In this case, the equipment is set at 180 degrees Fahrenheit, so that would be the maximum temperature for our hot water heating system. Now, the last major piece of information that we need is the volume of water in the system. It's a rather tedious calculation, but ultimately, someone has to do the calculation or do a good estimate in terms of how much water is in the system. For my imaginary office building, I have estimated the volume of water to be 2,000 gallons. So now I have all 5 pieces of information for making an expansion tank selection. So I'm going to go next to our system one more time to kind of go through all the numbers. I have a minimum pressure at the expansion tank of 40 pounds and a maximum pressure at the expansion tank of 110 pounds. I also want to point out that the expansion tank is connected to the suction side of the pump, and that connection, the point at which it connects to the piping system at the suction side of the pump, is called the point of no pressure change. And we recommend that the expansion tank always be connected to the suction side of the pump for the best system operation. Okay, let's go to the
Before you do that, Rich, can you just briefly suggest how folks should calculate the system volume, or methods that might be used?
Manually. If you manually calculate the system volume, what you're doing is you're taking, in our case, let's go back to the system diagram for a moment. You would have to take all the piping in the system and determine what its volume. There are plenty of charts and graphs that'll show you what the gallon is per linear foot for each size pipe. I don't have the numbers right in front of me, but let's assume that you have a certain size pipe and it's 1 gallon per linear foot. And if you had 100 feet of that particular pipe, then you'd have 100 gallons. So you have to take the volume of all of the piping system and all the equipment, anything that adds volume in terms of water to the system, you'd have to add that up, add a safety factor, and that becomes your system volume. Now you can do that either manually or There are very sophisticated software packages out there. We have one that we use called the Hydronic Systems Solution software package, which will calculate the system volume if you use that software. So you can either do it manually or use the use of software, but ultimately someone has to come up with the system volume. Hopefully that answers the question. So now we're at the expansion tank app, and here you can see that all you need to do is fill in those 5 pieces of information. And I'm going to go to the next slide rather. And here we filled in the volume is 2,000 gallons. The minimum temperature is 50 degrees Fahrenheit. The maximum is 180 degrees Fahrenheit. The minimum pressure is 40 pounds per square inch gauge, and the maximum is 110. By the way, you can see that I've selected clean water, no glycol, and that the piping material is copper. If I go to the next slide, I click on the search button, and now you can see that the software, look on the window on the left-hand side, and you can see that it has calculated the specific volume at the minimum temperature and the specific volume at the maximum temperature. Between those 2 values and the volume, the system volume of 2,000 gallons, the software has calculated the expansion, and in our case, it's a little over 53 gallons. We're going to ignore the plain steel tank at the bottom of that little green box, and where it says required tank volumes for the bladder style tank, it's recommending a steel tank of at least 95 gallons. So if you look at the right-hand side where it shows the results, it shows that a CA 450, which has a steel tank volume 119 gallons, it shows the acceptance volume of 119. The acceptance volume is a full acceptance tank, so it's the same volume as the steel tank volume. And we can see that the acceptance volume has to be greater than the expansion volume. The expansion volume, again, was a little over 53 gallons, so that first result or category, specifically, selection for the expansion tank will meet the requirements of this project. So I'd like to go next to our home page, and on our website, if you go to our home page, you'll notice at the top it says takocomfort.com. I'm actually live right now in terms of our web page. If you go on the left-hand side of our home page, about halfway down, you can see apps. If I click on that, there's a drop-down menu that occurs next, and if you'll notice, I will click on expansion tanks, and now you can see the expansion tank app in real time. I'm going to fill in the data that I just did for our example to reinforce what we've done here. So I'm going to put in 2,000 gallons for the volume. The initial fill temperature is 50 degrees Fahrenheit. The maximum temperature is 180 degrees Fahrenheit. The minimum pressure or fill pressure is 40 pounds per square inch gauge, and the maximum pressure is 110. Now, if I scroll down just a little bit, I can click on the button where it says search. And when I do that, again, this is a repeat of what we just selected. Just resize the screen here so you can see the full thing. Okay. Hopefully everyone can see that. Again, Brett, hopefully you can see my cursor moving. Just let me know if that's true.
Yes.
So I'm pointing now to the expansion volume, just over 53 gallons. So the software has selected a tank. The required volume needs to be over 95 gallons. It has selected a tank of 119 gallons. Since the acceptance volume in this case is equal to the tank that's a full acceptance bladder. And so that first selection will do the job. I'm going to skip over the plain steel tank for a moment. If there is a question about plain steel tanks, we'll hold those to the end. If you'll notice the third selection down, it's a different style tank. In this case, it's a CBX, which is a partial acceptance volume. If you'll notice, the tank is 112 gallons, but the acceptance volume is 61 gallons. That means that this tank has a maximum bladder capacity of 61 gallons. Well, since our expansion is only 53 gallons here on the left, this tank also works as a selection because the tank at 61 gallons acceptance is greater than the expansion volume, so the tank will work fine. And I'll show you one more selection, and it's the fourth one down. In this case, it's a smaller tank, but there are two of them. And if you'll notice, the tank volume is 57 gallons. Well, as a single tank, that would not be enough because it needs to be 95. Well, 57 times 2 is 114 gallons, so 114 is greater than 95, so it meets that criteria. It's a partial acceptance tank. One tank will only hold 27 gallons, so if I multiply that by 2, that should come out to 54 gallons. We need just under 54 for expansion, so that tank would also work. Okay, one of the things I want to point out is that I'm going to write down next to my desk here just so I don't lose the size. The expansion, when we have water in this system, is just over 53 gallons. So I'm going to write that down here, 53 gallons. Let's assume that you went ahead and made that selection, but someone made a mistake and they did not select the fluid properly. They did the calculations based on water, but the actual fluid in the system was a water glycol. So if I go to the drop-down menu for a moment and I pick propylene glycol, and let's assume that someone wanted a concentration of 50%. This is after the fact of making the initial selection. If the actual fluid in the system was 50% propylene glycol, click on search. If you'll notice, what happens is that the volume is now 90, the expansion volume is now 90 gallons. And in the original one, it was just over 53 gallons. So the point is that if I did all the calculations based on water, but in the field, they filled the system with a water glycol solution, not realizing that the selection was based on 100% water, they would not have enough expansion tank capacity because the water glycol solution in this particular example is going to be an expansion of 90 gallons. So not quite twice, but almost 2 times the expansion of just straight water. So it's very important that someone figure out what the fluid is in the system before they go through and make the selection, because if you make the selection on water, but in fact it winds up being water glycol, you potentially could have a problem with not having enough capacity in the expansion tank. So I'm going to switch back to water for a moment and just recalculate, and it drops back to 53.44 gallons of expansion. Now, the other thing I want to point out is what happens if you put in a different system volume? Well, I estimated the system volume for my imaginary office building to be roughly 2,000 gallons. So what if I was 4,000 gallons? Well, it turns out I'm going to just change that to 4,000 gallons, and intuitively you would expect that 53.44 to double, and you would be correct. So that means it's going to be roughly, let's say, 106.8 gallons. So I'm going to click on search down here. You're going to see that it's 106.88. So if I double the size of the volume, it's going to double the expansion, and the expansion tank is going to have to be twice as large. Now, here's an important concept. You can make the expansion tank larger than what you need, and there's no penalty to the operating characteristics of the system. The penalties are in physical size and cost. Obviously, if you're overestimated the system volume and you make an expansion tank selection that's larger than what you actually need, you're going to pay slightly more for the expansion tank. And because it's physically larger in physical dimensions, there could be a problem installing it in the mechanical room. But there's no negative effect on the system operating characteristics. So one of the things, in order to be very conservative, that people tend to do is that they will oversize the expansion tank, knowing that it has no negative effect on the system as long as they pre-charge it to the proper minimum pressure. The maximum pressure that will be reached in the same exact system will be less than the design pressure. Okay, one last concept I wanted to point out. If the expansion tank was located at the bottom of the building, as we've suggested in this presentation, the minimum pressure would be 40 pounds and the maximum would be 110. If I moved the expansion tank to the top of the building, then a minimum pressure would be approximately 7.5 pounds and the maximum pressure is 110. Whoops, let me get my calculator out here. Would be 110 minus 32.5, which is now 77.5. So I'm going to go back to my original example here, change my 4,000 gallons into 2,000, just to make sure that I have the same selection as I had before. That's correct. But now I'm going to leave the temperatures the same and the volume the same. I'm going to change the pressures. Now my minimum pressure from 40 pounds to 7.5 pounds, and my maximum pressure is going to be 77.5 if I was at the top of the building. And then I click on search. The same expansion, see the fluid has expanded the same exact amount, 53.44, but now I need a smaller expansion tank. I no longer need an expansion tank that's 95 gallons or greater. I only need an expansion tank that's 70 gallons or greater. So whenever you move the expansion tank from the lowest part of the building to the highest part of the building, the expansion tank gets physically smaller for the same exact set of parameters, with the exception of that the minimum pressure or fill pressure at the top of the building, in our case, is 7.5 pounds, and the maximum pressure, we want a maximum of 110 at the bottom of the building. That means the maximum we want at the top of the building is 77.5. So when you move the expansion tank physically to the top of the building, the expansion tank gets physically smaller. And a lot of people will do that to save on the size of the expansion tank, especially in very tall buildings. Okay, we're just about at 11:50 at this point. Brett, do you have some questions that may have popped up during the presentation?
Yes, I do, Rich. Quite a few folks asked about when do you choose which expansion tank for what application? When would you choose a full acceptance over a partial?
Well, again, let me point out that the full acceptance expansion tanks are the most reliable in the sense that they're somewhat foolproof. In other words, if you had, as I said earlier, a 100-gallon expansion tank, if you had a full acceptance, that means the bladder can expand to the full volume of the tank. So if something should go wrong, let's assume for a moment that the tank, when they went to pre-charge the tank, let's assume they got the tank in, and things like this happen. We've seen it happen. Someone might take the Schrader valve and relieve the pressure for maybe, I don't know why they would do something, but maybe that happens. Who knows? So if they do that, maybe they take the core of the Schrader valve out and the air side of the tank goes to 0. Again, this is before you physically connect it to the building. So instead of having a pre-charge pressure of 12 pounds, now it's got no pressure. Now you connect it, but someone forgot to pre-charge the tank and the air side is open to the atmosphere. So they connect the tank to the system, and guess what? It's not going to take a whole lot of pressure to expand that because there is no pressure opposing the expansion of the bladder. So the bladder expands and expands and expands, but it can only expand to the full volume of the steel container. So a full acceptance bladder will not rupture. However, if it's a partial acceptance bladder, you run the potential under that scenario of the bladder expanding beyond its capability. In our case, we said if you pick the partial acceptance, perhaps the acceptance was 61 gallons, and the tank can hold approximately 112 gallons. So in our case, if someone had inadvertently let the air out for some reason, it would try to expand to the full physical volume of the steel container. And since it's greater than the acceptance volume, the tank bladder could potentially rupture. So it's safer to pick a full acceptance bladder. So why doesn't everybody pick full acceptance bladders? Well, the answer is simple. They're more expensive. So the larger bladders are more expensive than the partial, and then the least expensive one is the diaphragm, but the diaphragm cannot be replaced, and so you run the risk of, if that was inadvertently expanded beyond its acceptance volume and it fails, then you have to discard the tank because you can't replace the diaphragm.
In other words, they all work. They just need to be sized properly, installed properly, and for your application, any one of them potentially could work. We have another question, or a good question here. If the system has a thermal storage tank, does it need an expansion tank?
Well, any system that has a difference in pressure, including a thermal storage tank, the assumption is that the thermal storage tank has been filled to capacity. There's no air volume in the storage tank. If there's a change in temperature, the fluid will expand. It has to have a place to go, and so therefore it would need an expansion tank. Keep in mind that if you do not have an expansion tank, as the fluid begins to expand, one interesting characteristic about water, it's called an incompressible fluid. You only have to change the temperature a few degrees. It will break whatever container the water is in. So when it comes to a hydronic system, the weakest part of the system will break first, and usually that's things like air handling unit coils or boilers or something else. Pressure ratings on piping is usually higher than the pressure rating of the equipment in it, so usually there'll be a catastrophic failure of a piece of equipment if there's no expansion tank in the system. Any other questions?
Would you recommend installing an expansion tank on a chilled water system?
Yes, always have an expansion tank, whether it's chilled water or hot water. So intuitively, you might say, well, the chilled water is running at, say, between 45 and 55 degrees, and the fill temperature is around 50 degrees. There's not going to be any real expansion. Well, you have to think in terms of worst case scenario. Worst case scenario is that you might fill the system just like a hot water system with 50-degree water. You expect the system to operate between 45 and 55 degrees perhaps. But you can have a case where you fill the system on Friday, they pressurize it, they purge all the air out, it's filled with water at 50 degrees, but the chiller is not going to be started up for another month, and it's going to sit there in the middle of the summertime. And let's assume it's the month of July. Where I live in New England, we can get temperatures that can exceed 100 degrees. And so the building and the water is just sitting there heating up and heating up. So its maximum temperature might be closer to 100 degrees under that scenario, in which case the fluid will expand. If it has no place to go, it'll break the equipment in the system. So yes, chilled water systems should always have expansion tanks, and they should be sized for a maximum temperature of around 100 degrees to be safe.
And you can use more than one expansion tank, correct?
That's correct. You can have as many expansion tanks as you like, as long as they're piped in parallel with each other and that the safety valves are in the proper location. Then you can have as many as you like. I was involved with a project out in Pennsylvania several years ago, and I think they had 4 1,200-gallon expansion tanks for a campus distribution system.
It's my understanding too that our expansion tank, especially the full bladder, have a valve at the bottom. Excuse me, a fitting at the bottom, and a lot of times the contractor will connect to that fitting, and they should not. It ends up if they put a ball valve on it and it leaks by, or eventually it's going to leak by, and it could really damage that tank. So, or the bladder, excuse me, the bladder. So that's a big problem. There's a plug on the bottom, and we've had many cases where the contractor added an unnecessary ball valve to the bottom of the tank. So that's right. That's something you got to be careful of. Can you pre-charge the system after the tank is connected in the system?
No, you cannot properly pre-charge your tank when it's physically connected to the system. You always have to disconnect the tank from the system. You have to drain the water side of the tank, and then you pre-charge the air side to the minimum or fill pressure of the system. And in our example, that would be 40 pounds. Then you connect it back into the system. So never pre-charge the tank after it's been connected to the system.
All right. Thank you, Rich. We're winding down here, and if we didn't get to your question online or live here, we will answer them directly. So keep that in mind. And we do want to remind everybody that the presentation will be available to download, as well as your PDH credits, and the video will be available as well. So, Rich, you have anything in closing you'd like to add?
Only that we have a very robust app for selecting expansion tanks. You can do your initial selection using our app. You can also, as I mentioned a moment ago, you can play what if. What if there is a water glycol solution? How is that going to affect the size of my expansion tank? And the app does give you multiple selections with different sizes, so you can use, perhaps you have a dimensional restriction. Maybe you're dealing with an existing mechanical room that has a door that has a maximum opening of, say, 36 inches, and a single tank might, I'm just making up some numbers here, a single tank might have a 40-inch diameter. You can easily put in 2 tanks with a smaller diameter and fit through the existing door. So the app is very useful, quickly selects the expansion tank, and allows you to change the variables so you can see what effect it will have in the expansion tank in case you have some other criteria that you're trying to meet.
And can that app be used for domestic?
In terms of domestic water, yes, but domestic water has some other criteria relative. The expansion tank itself has to be rated for domestic water. So, for example, if you scroll down in my, I'm going to scroll down, hopefully you can still see my screen, Brett. At the bottom, the PAX tank, PAX-425, that tank is specifically designed for domestic water application.
Thank you, Rich, and thank you everyone who attended. Hopefully you got something out of it. And now the expansion tank won't be the mystery in the system. It is a very important part to a hydronic HVAC heating and cooling system. So hopefully this clears some calculation things up for you. Be alert, be on the alert for an email thanking you for attending, as well as with the links, and look forward to other TACO Tuesday classes. The next one in February will be an introduction into the HS2 software, a design tool that allows you to design or helps you design HVAC hydronic systems that you can download from our website, and we'll get into a lot of details in that as well. Other than that, Rich and Brett are signing off. Rich, I'll say goodbye and then take it away.
Thank you, everyone, for attending our webinar. We really appreciate the opportunity to show you this technology and our expansion tank concepts and how to select an expansion tank using the TACO expansion tank application. So have a great afternoon, everyone. Hopefully you're in a part of the country that you're not being buried by snow, and you can enjoy the rest of the week. Thanks again.